Okay. Today I'll be covering writing a compute shader with OpenGL. We'll be writing it from almost scratch. I will be using the tutorial provided by Anton Gerdelang. Here is its link. It seems like a solid tutorial. I hope you enjoy it as much as I do. I'll also be writing all the boilerplate code that is related to compute shaders in OpenGL. Okay. So in order to write a compute shader, you need to outline a texture. The basic thing you have to have in order to write a compute shader is, of course, first a modern OpenGL context that supports version 4.3 or newer, or something more new. The other thing you need is to have a boilerplate on loading textures. We're going to go ahead and compute that for this session. I already have something called texture CPP, which has almost all the boilerplate. And I will be writing it again from scratch as well, in order to stay true to the text provided in the tutorial. Let's go ahead and say something like simple compute. Loaders are of course necessary. Okay. So these are all the packages that I use tutorial. The file system to access the path and other folders and files in file system. This is necessary. I put my shaders in a directory called shaders. Oh, so surprising, I guess. So these files are they need to be specified with respect to the executable you have. For example, my shaders are given relative to the executable. The bin file contains all the executables that will be using the media provided as accompanying to executable. For example, if I want to use the picture of one of the textures I'd like to use, for example, to use a texture specified in here, I need to provide path to this texture with respect to the executable using that texture. Here, for example, let's see what texture out gives us. Let me just show you right away. So here is what texture looks like. I need to specify this texture. Here is what the executable gives when we launch it. This texture is specified in the media directory. It's actually the Stone diffuse, if I'm not mistaken. Since since the location of this texture is specified within the code with respect to the executable we have, we can load the texture in runtime. And that's something maybe not the best thing to do, but it's quite handy for testing shaders. Again, not very good for production, I know, but if you just want to test a couple of shaders like I do, that's what I do. Hi Tahsin. Thank you, it's a lovely day again. Alright, let's continue with the compute shaders. Now, as I stated, again, we just need a boilerplate to load textures to the screen. I can already copy paste my C++ code directly, but I'll be covering it line by line. It would be a little obvious what it does, but still. Commenting it line by line. Basically here I'm giving the window width and window height. I'm declaring some global variables. Here I'm calling a context version, but this is actually not necessary. I can specify it my main call directly. We're going to be using 4-point major 4 and the minor 3. This is quite important because compute shaders are added to OpenGL with 4.3 above. Okay. This is what the window manager would do if we resize the window. We won't be using any keyboards or anything that's interactive, so I won't be loading this all of this keyboard related stuff. And texture loading, we won't be covering that as well here, because we don't need it so much, not yet. Or at least to demonstrate the basics of the compute shader, we won't be using this, but for production code we would need this absolutely. But I will be skipping this as well. Now let's see what we can do. Let's start with our main function. Okay. This is the classic main function for OpenGL shaders and for most of the graphics programs. As usual, we have a main function which gives out an int that no one really uses. We're declaring it that anyway. Again, 4.3 necessary. Context initialized. We declare the window, of course, with the given variables above. Let's call it something more sensible, like compute shader window. Okay. If, of course, the classic if check, if the window is unavailable, this is the famous null pointer that gives everyone headaches from time to time. We simply print out failed to create, failed creating window, and print the end of line and return -1, meaning that -1 usually means that we had an error in the program, and the 0 mostly means that everything went good. Okay, so we make the window current context. That is, we make the window the context we will be drawing on. If we resize the window, of course, we set a callback to simply resize the window easily. We declared this callback above, might have guessed. It simply resizes the window to the new height and new width that it takes as an argument. And we use the glad here. Glad here is an OpenGL pointer. It's helped us to use OpenGL in different systems. Of course, this should be here. The glad should be included before glfw, though the formatter doesn't really enjoy this. I keep rearranging it. We have to make sure that glad is loaded before the glfw. It's one of the, in most cases, when the compiler complains a lot, it means most probably that I forgot to load the libraries in good order. Okay. We give default viewport, of course. So it starts from 0, 0, and right. I'm basically writing most of the boilerplate necessary for compute shaders for now. This is not a code that really calculates stuff or anything, but this is necessary for all kinds of compute shaders we would like to use afterwards. All right, so let's see if okay, you guys wanted to, let me see if I can find some kind of link for you guys, and share the link of all right. Here we go. All right. So let's get back to our shader code. We need to specify the vertices. That's very much important. We won't be using like a lot of normals and stuff like that. I'll be using simply square and putting the texture coordinates directly there. So my vertices would contain the vertex positions in screen coordinates, not the colors, we won't be using them, but also the vertex texture coordinates. Some of those who follow my my sessions know that I tend to explain a lot of things at the same time, but as you might have known, the model coordinates are given in range -1 and 1, and texture coordinates, the texture spaces between 0 and 1. So this is why we have at the same time two spaces stack in the same vertex array. Okay, so we have texture coordinates right here. Now shader loading part, I'm going to come to that later on. For now, let's just specify the indexes, that is the drawing order for these vertices. And if we look at the indexes, the first triangle is 0, 1, 3, meaning that it's going to take the first row, second row, the second row, the third row for the first triangle, and afterwards it's going to take the second row, third row, and the fourth row during the drawing phase. Alright, so let's write the necessary objects, the classic VAO, VBO, EBO, and most of the other related code. These are all objects. Like VAO holds the array information, it holds the vertex data. VBO is the buffer that holds the data, and EBO contains the information with respect to the drawing order, with respect to the indexes we had provided. As usual, the OpenGL API wants us to specify like the classic OpenGL API, classical functioning in the OpenGL API is that you generate something, you activate it, and you like bind the data to it, and you deactivate it, and that's like the classical procedure for most of the OpenGL structures actually. And VAOs are not really an exception to this. We bind the vertex array that we are going to use, meaning that we want to do like we want to process information with respect to this. We bind the buffer, it's the array buffer, and once we have the buffer, we simply bind data to it. Static draw. Buffer data. Okay. This is our main function for now. We are going to, of course, need the element array buffer. As you can see, the procedure is almost the same. We just specify a different buffer for activation. And we pass the indexes to the buffer. Yes, to the element array buffer. Static draw. Alright, so we're going to, of course, use pointers to process the vertices we just specified. Vertex attribute. GL float false, and the stride value when the next value comes, it's 5 size of float, and this void cast is not very pretty, but that's like the only choice we have when we're using OpenGL API. It's basically the offset value we need to specify. Let's see if you guys are saying anything, and we continue. Since I skipped the color attribute, I won't be using that. I won't be needing to point that, but I will need to specify the location of the texture coordinate. So vertex attribute point float false 5 times the size of float. Another void cast again. Size of 3 times the size of, because it's about offset, not about stride. So, okay. Of course, if we want to squeeze out the best performance there is, we can create a variable for holding 5 times size of float and pass that variable as as an argument to these functions. But I don't think the overhead for 5 times the size of float is that much, to be completely honest. And we enable the attribute as we load it. Vertex attribute pointer. Okay, so this should be like the most basic, like the bare bones of the vertices we had just provided. So now let's start to follow the tutorial I just linked to and see if we can actually use compute shaders in OpenGL. As far as I can see, the compute shaders are the only ways you can like gracefully implement ray tracing and other types of pipelines. That is, they are the only not the only means, but they are the most elegant way to implement the rendering equation, which you would need, which models the light transport in a scene. Okay, so let's see if we can like follow what had been given in the tutorial. I will be sharing the link of the tutorial in the source code as well. Not the best practice, I know, but still. It should be visible. No. We specify the width, texture width, let's say. Something like window width, since it's going to cover the full screen. It should be using the window width. And texture height. Right. And we create the classic texture object. Texture output. I'm changing the variable names that's being used in the tutorial in order to internalize a little more what's happening in the code. Texture. So we, again, the classical model of OpenGL API, we generate the texture, we bind to it, and we add data to it. That kind of never changes. texture 0. This is more or less the same thing when we said the bind GL array buffer. Instead of saying bind GL array buffer or specifying the buffer type, we simply specify the texture, the available texture slot that we would be using. OpenGL. Again, we bind to it. Up. Text 2D texture output. We give like simple parameters to this texture. So text create a couple of them. Text wrap S, clamp to edge, edge, for T we do the same thing. These are not very important parameters for our case because it's not like we're doing something complex. I'm trying to use the most basic options that are available. Mac filter, GL linear, min filter is also linear. Let's see. Okay. So we create the image here. Well, we create the image basically meaning that we are going to be creating something completely black. Texture 2D 0. This might be the only thing that's a little more different than what you usually see. In most cases we just use GL, RGB, RGBA, and we pass on to something else. But here we are using specifically floating points and 32-bit floating points. Okay. I forgot the value of an argument here. GL float and null. So this seems like the arguments provided in the tutorial I'm following. Oh, okay, well. Then we use a call that we don't really use a lot in other OpenGL related code, rasterization code at least. We use a call called GL bind image texture. Okay. Output. False. Okay. Right. Okay, so we try to write to a texture because okay, we will be using values stored in this image while we're doing calculation. Texture. Texture handling work group. These are all variables that are related to compute shaders. They they help us to divide the workload between different compute shaders. Right. Okay. Okay. Max compute work group count. Go. And we basically do the same thing for 1 and 2. This is not the size, this is the count. Size is something else. Okay. We can print this information on the screen. Let me see. Let's print these information on the screen as well. Photo. We're going to do the same thing for workgroup sizes. Let's see if there's anything. Okay. Workgroup size. No. Workgroup size. Okay. Again, we print out the information. Yes. Okay. Then what? Then what? Let's use different texture dimensions provided. Let's use the texture dimensions provided in the tutorial. Since the window changes, since we can resize the window, some of these workgroup counts and sizes might change unexpectedly. So now we have work group size, meaning that texture right and global, and 20 seconds for the eyes, people. It's very important. Local work group size 1, because we're going to be covering 1 pixel at a time. Okay. Now we can also specify the invocations as well, but I'm not seeing any code with respect to that in the tutorial. Well, for now, let's follow blindly what the tutorial says, but I'm not very happy with this. File of jobs and 1 local work group. Then okay. Hmm. Okay, let's write the rendering code for now. The GLSL code for now. See what would it give us. Later. Good. Compute. Yes. Version. Yeah. One. Okay. RGB binding 0. Okay. Kernel format. Let's add some comments to remember later on what each of this does. Name as local work size. Pixel all black. This is very new to me, to be completely honest with you. I can vaguely understand what's happening because I kind of know how ray tracing works. I'm just assuming that the API here follows the model of the equation of ray tracing. To compute. But the API structure is a little strange for me as well, because the ray tracing API is quite different from rasterization API. In rasterization, we can treat the illumination as a function. We can treat the global illumination as a function of the object. That is, we can treat all the illumination as a form of scattering. But ray tracing shifts our vision to consider illumination as a phenomenon of light transport instead of just surface or subsurface scattering. So, the API structure should be quite different than the usual scattering, and that's what I see here. But since I'm more or less accustomed to work with the rasterization API in OpenGL, I am kind of out of my I'm not very comfortable with the code I'm writing for now. Okay. So this is the general structure of the shader we would like to achieve at the end. All right. Okay. Let's continue writing our program. So, classical rendering part program. So, for rendering call, or the update call, whatever you want. Okay. We of course declare the shader as well before we start rendering stuff. Attach. Create shader. We create a compute shader. Yes. We need to read this file. Let's create the file path first. Is all shaders are shader their path, and shader path. Let's see our shader class to peek how we can load shaders. This is not very important. These are all helper functions. What's important is the load shader function. Let me just write a quick function like here for loading shaders. "20 seconds for the eyes again, people. Take care of your eyes, it's very important." Okay, let's write here shader code. This is basically a C string. Shader type. And of course the shader. Create the shader. But we don't really need this actually. We just need to load the string. Can we pass string values in C++? I always forget this. Let me see. Let me search for it. We can pass arrays to Okay, so Herb Sutter says that we can actually um, return strings. Okay. Great. Uh, focus on lot of things, lot of things. C++ can get complicated. It really can get complicated. Oh. For our case, let's say let's do this. Shader code string. Uh, a lot of stuff. Mm, this is okay. Hmm. We don't have SS streams here. That's why. We have the F stream, iOS stream, string stream. Okay. Let's say load string path. We don't need the shader type. Alright. Let's see if anyone's asking anything. Okay, let's continue. So, so now we have a code that should load the shader file from the given path. So we had declared the shader as compute shader. We have a path here. We're going to need the shader source string shader source load string from path. load string from path, takes shader path argument, and we can continue following the tutorial. So we declare the shader source as shader source, shader source, gray shader 1, let's string const array shader source string the string shader source pass shader source and null pointer compile shader we can of course check for the compilation errors. Check shader compilation. This is a very basic function to check for shader compilation errors. Takes the shader and shader type and simply outputs some information about the state of the compilation of the shader in question. Gray shader and compute. Okay. Then we create a program. Create program. We attach shaders to the program, of course. Shader. Then we link the program. Now let's check for linking errors and related program errors. This is simply another function that checks all of those. It outputs success, or it prints simply some information about the program on the terminal. It prints the status of linking of the program. Okay. What what are the basic differences? C++ have some more structures than C. C++ is designed as the superset of C. It has templates, classes, and other object-oriented data structures that are not very much that are not found mostly on C language. So that can be stated as the basic difference between C and C++ probably. Most of the programs you write in C works on C++, of course. For raw performance, it is stated that C performs better than C++, but for most modern architectures, there's very little difference between them performance-wise. The good thing is that, well, it doesn't help so much in OpenGL, but the good thing is that using C++ as your language gives you the ability to organize your code in object-oriented structures, which is from time to time nice. But since OpenGL, anyone who knows C can learn C++ in an estimated time. I would say anyone who's like familiar with C can learn C++, and I would say like if you're trying to develop the same kind of software you're developing in C with C++, it wouldn't take so much time because you would simply be using the same set of features you use in C. If you would like to use like object-oriented part of C++, it depends on your experience with languages that has that ability. So I would say that if you have an experience with object-oriented languages like Java or Python or any other stuff, I would say you can learn let's say you can be efficient. Not efficient is not the best word, but you can start to use C++ like in 2 or 3 months. You would be familiar with the structures anyway, and to get really like into the advanced stuff with C++, that really depends on the type of problem you have, and it can take from like a couple of months to like 5 years, 10 years or so. It's I had read somewhere that learning C++ is a 10-year endeavor. I think it's a bit of exaggeration, but still for some problems. Okay, that's good. If you know Python and OOP, that's good. I would say like you can learn C++ with no like problem. The thing that's not very easy to do in C++ is that most of the structures are iterators, and you need to like learn to work with iterators. Especially in the standard library, it's mostly like iterators all the time, streams, iterators all the time. But if you know if you know C, you can basically like work on your C knowledge and like try to develop that into like if you already know C and OOP, you can learn C++ with no problem. Like you just need to like start with a couple of basic programs to get your feet wet with the OOP structures and C++, and that should be it. I would again say like in 2-3 months at most, you would mostly be familiar with the OOP structures of C++, and the rest is just making more projects, developing more projects with C++. That's what I can say. All right. So we validate the program and we start the rendering call. That is dispatching of shaders. We use the program. No problem. Thanks for asking. Good. This is a unsigned integer cast. Texture with another unsigned integer cast. The syntax for casting values is not very jolly. I don't like casting values in this syntax, but well. It seems like it's a macro rather than a function. Launch shaders and launch shaders. Basically, we need to make sure that writing to the compute part is finished by creating a memory barrier. And we do the normal, like the classic drawing pass. With clear color. Clear color. Buffer a bit. Of course, we need to shade the okay. We need to load a couple of more shaders to the program before we can like actually do anything with it. So this is the get shader. Compute shader part. Let's write the quad shader. Quad basically means it's going to fill the entire screen. That's what it is. And Let's. I probably already have something very similar to this. So let me check if I have something similar to this. Okay. Great. So I kind of have something similar to this. That's great. I'm just going to use compute vertices. A post export, and I probably have a frag version of this thing. As you can see, I tried a lot of stuff before. Let's get rid of all this. This as well. For this compute frag, we won't be using my color. So in, out, frag color. In text chord, we won't be loading any textures. Or should we? Or should we? Yes, we would be loading some textures after all. The texture we just declared in the code, we will be using them. That's one. Okay, so I have a basic texture with my texture and text chord incoming from the vertex shader. Okay. Let's these are basically our quad shaders, things that are going to fill the entire screen. This is the fragment shader. It just takes the texture coordinate and fills the screen with texture. And this one, let's declare these shaders right away. Let's call this compute shader path. Okay. For this, we can probably use the shader class I have written. Already. So let's use that instead of writing an entirely different thing. Up. Custom shader. Okay. My shader, what the shader class does is what you had already seen. It just loads the texture and checks a couple of things. it attaches, or let's not use the shader class, and to make the code self-contained, let's not use the shader class, but try to create a quad shader that's going to take the vertex and the fragment shader as its argument. So recreate the quad vertex shader first. Shader. And the quad fragment shader. Fragment shader. Then 20 seconds for the eyes, people, again. Then we compile both of them. We load and compile both of them. Vertex source. We should specify the paths, of course. Fragment. Fragment. Let's see if anyone says anything. Nope. We continue. We load, we source these shaders, of course. Then we compile them. Let's first source the quad vertex shader. Let me check the... Okay. And we then source the fragment shader. And lastly, we attach these shaders to our program, which we are going to call quad program. Surprise, surprise. Where program. Create program. First we attach all of the programs, then we link them. Quad program, quad shader, F shader, then we link the program. Let me just verify that using my shader class. Yes, we attach both, then link them. Then we can delete them or not. That's optional. But let's keep them. It's not like they're going to hurt us. But we can delete them once we attach them, actually. Okay. Quad program. I'm going to use the same drawing call in my as in my texture CPP file, which was draw elements. But before that, let's bind the texture. Bind vertex array. Texture. texture 2D. And yes. Then we poll the events. We check for the closing. We want to eventually close the window if it's necessary. So okay. I should change my completion manager. This thing's getting really boring. Okay. Now this is the regular, this is the regular program. Let's return to our compute shader and try to modify the GLSL code. Compute. Yes. Now here I've written stuff to compute. Now we are going to fill that thing, hopefully, and obtain something like useful. Okay. Okay. So not the best strategy, but we're going to hard code the scene to our shader. I'm going to need to find a way to use that thing in an interactive fashion afterwards, but for now, since I'm not very familiar with the API as well, I'll be following the tutorial here. Glsl index x to x, or let's use image dims. Dims. Dim. Let's do the same thing for y. Why are we doing this? Because we are trying to come up with the line equation here. I'm assuming that's the case. So grade destination. In an orthographic projection, in at least we're not covering like perspective projection, but we're going to cover orthographic projection. We can say that the destination simply -1, because all rays would be pointing forward from the camera. Let's have a sphere in the scene, or at least something in the scene, and let that something be sphere. We give the sphere center as a three-dimensional vector. And the radius of the sphere is equal to 1. It can be a little bigger, but let's make it equal to 1. Now all points on the sphere has the same distance to all points on the sphere has the same distance to the center, which is the radius. All points on sphere and the ray is on the same line. Okay. Good. Okay. So we're going to need to check if the ray interacts with the sphere. Good. 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 Basically, there are three cases possible. Miss case, intersect case, or tangent case. Basically, the ray hits the sphere on 2 points, the ray hits the sphere hit on 1 point, hit on 2 points, hit on 0 point. There are basically two cases possible. Okay, so let's do some math here a little, or let me just transform the math that's provided in the tutorial to code. Points on here, d minus here, center, minus r radius here, radius is equal to 0. Array, or any point array, let's state it this way, array direction equation point, any point on ray is origin ray times plus direction of ray times some length of ray. Magnitude, let's say. Point any point on array can be summed up as, this is basically the line equation. So in order to check if the ray intersects with the sphere, we simply put the point on ray, substitute the point on ray to the point in the sphere's equation. So we check if origin of ray plus direction of ray times magnitude, all of this, minus sphere center minus sphere radius is equal to 0 or not. Yes, this is it. So in this equation, we know several things. We know the origin of the ray, yeah, we know the origin of the ray, we know the direction, we just don't know the magnitude, and we need to find out the magnitude. We can say that origin of ray minus is equal to sphere radius and say this. Let me see if I can find a better solution to this. Linear search first book. Let's see. Okay. This is like the basic linear algebra. I'm trying to find out if there's there's already an computed version of this equation. Yes, line. Yeah, we basically expand this into a quadratic. Which goes into let's use better 20 seconds for the eyes. Let's use better variable names. Let's use O plus D times M minus C is equal to square is equal to R squared, meaning that is equal to R squared plus dm minus c again R squared when you expand this yes it expands into something that's not very funny. It expands into e squared times m is 2d m times plus squared. I can vaguely see the uh, The quadratic formula here, I can vaguely see it. Is equal. Both of them are equal to r squared, of course. We're trying to find, like, formulate the equation in this sense. So we are trying to obtain this in order to have a solution. And we almost have it, I think. This is m squared. So basically a is m squared x is d x is d, yes. And b is 2 times m times o minus c, and c is o minus c squared minus r squared. So we have the quadratic equation, which can have two solutions, of course. Can have two solutions. We were looking for m, We can take, of course, either D or M as the X, and use the other one as A. I'll be right back in a second. Let me. I'll be right back in a second. Let's see. Where were we? All right. Let's use D and M. All right. So this means that M is equal to minus B plus let's see if I have that sign. I don't think that I do. Think for a sign, but I don't think that I have the necessary sign. Ah, this one. Plus minus. The square root of b squared minus b. And if they are in the same direction, if they're in the same direction, we might have a tangent. Okay. Section. Equals to 0. So these are all three possible cases. We are going to simply test these cases while we are computing whether we are hitting to the sphere or not. Let's see if anyone's interested. Okay, let's continue. So let's compute the terms of this equation. Let's get C and B. The float. What do we say? No. C. I don't know. Something. Origin of. Do we have that yet? Center, sphere center. Ray O. Yeah, we have that. Ray O minus sphere center. the ray to sphere, let's say, and this is a vector. We should have the code C by now. Just dot ray to sphere with itself. Minus so this is C. Let's get B. B was 2 times the dot between ray direction and ray to sphere. This was B. Now the result variable B minus B2 B is and we check for the miss case. For let's say you'd have like a whitish, a grayish pixel for those who are hit by the beam, by the ray. If nothing is seen, it's basically black. So this should be the overall structure of our compute shader. Let's see if we can compile this thing. And hopefully, not so sure if it's going to run at the first time. Hopefully we would be able to at least compile it. Let's add our executable. Simple compute. Okay. All right. Um, let's fix the. What the hell is this? I don't remember putting stuff like GL, GLH, GL text, and stuff like that. Did I really have this in my texture code? No, I did not. No, I did not. Okay, let's try to compile our code. We'll see if everything compiles well. Gives us a couple of errors, which is nice. Hmm. Didn't like what it did with the compute shader. Find image texture. Fairly sure this was what I should. GL bind image texture. Yes, it seems like the. Hmm. Yeah, it seems like we can use bind image texture. Bind GL bind image texture, yeah. Bind image texture. The core shader we are specifying is also uh, also be good. Core trees should be should get us going. Yeah, I forgot the recompile. Oh, same argument type again. Hmm. Hmm. Maybe I'm having a problem with the header. Uh, Let me generate a new glad class. Okay. Let me download these new babies. Let's see. Glad H. Yeah, this was a problem with my GL API version. Let's get rid of this and use this one. And let's glad h. And let's use the platform thing. This should be fine as well. Let's see. Let's see. We can compile our library. I see. We should change the Glsl to use glad we have provided. Now let's see what it gives. Compiles, files, simple PBR2, and simple compute gives error. But at least it gives nice errors. Maybe I think like that, but okay. All right. Why is it complaining? Ah, yeah, we're not. Yeah, I'm passing it by value. I'm passing it by reference. Okay. Okay. Hmm. I see. We need to change the string loading library to something else. Hmm. Let's see what we did in the shader. Okay. See. All right. Okay. This should be okay, more or less. I'm passing values. We're passing a null value. This should be okay, more or less. No. Let's see. And yes. And it compiles. Let's see what we're going to have as the output. Compiled. I'm not seeing anything. I'm probably not doing something wrong here. "20 seconds for the eyes." I'm coming right away. It's almost done. Hello again. We're almost finished with the with our compute shader tutorial. Not tutorial, but with our compute shader. Let's see. What are we missing? Workgroup count, workgroup size. We have batch compute. We are workgroup count, workgroup size. Dispatch compute. Use the array program first. Texture width, texture height. None of the dimensions are 0. Find the texture. And we call the array. We can simply call draw arrays as well. I haven't maybe Let me see my texture example. Maybe I'm not calling the correct argument here in the drawing. Fine. We bind the texture, we activate the texture, we bind the texture, bind the array, and we call the drawing call. Try that. What else can we change? Let's see what happens when we change the values in the Qt shader. Let's make this all reddish, for example. Yeah. I don't know if you guys can see this. So I'm seeing basically the values I enter here are seen by the window, by my compute shader. Just that it's painting everything instead of just painting the rays that are available. We change the size of the window a little, and nothing's really changing. Interesting. The nice thing is we can read the pixels. That's nice. We can draw. That's certainly good. That's certainly good. Gray direction. Urgent. Peer center. Yeah, this looks like it. This looks like it, but hmm, okay, let's see if it's related to invocations, which I don't think so, but trying does not hurt, does it? Beautiful. Let's yeah, it's just adding random stuff that okay. Hmm. local size x, local size y, binding 0, uniform image to the output, equals 7. We normalize the stuff here. What if we change the size, max x and max y? Play 2. Ranges 1 and 1. Nothing changes. 0, 1, 0.1. Nothing changes. Interesting. There's currently rain. It's raining so much here. Well, it's almost about 3 hours, and the worst thing is the code does not debug, does not give any errors whatsoever. But I'm not having a valid, what it seems like a valid, what it's supposed to be valid output. Some of the most interesting problems I had with the implementation of this thing was to make sure to have a good GLAD version, good API version. Let's say not core, maybe. Don't think so, but maybe. Never know. Ah, that as well. Local size x, local size y, in binding 0, uniform image 2D, 2D image output, void main, base pixel color, base color pixel, let's give this one as well. Not having any link errors as well. Maybe instead of using EBO, I should simply use VBO. Let's see. This one. Just going to draw a simple simple quad. Yes. No. the most basic example you can have here. Might just like pass a simple uniform. Not sure here. I'm going to have like a simple texture output. I'm not sure how to change the fragment shader to mimic the to accompany the compute shader. No, I was able to texture output. Let's see. Oh yeah. Array into this vehicle. Yes. I see. This seems like a mathematics problem rather than a programming problem. Let's keep everything in place. And keep this as this way. I don't think we're going to need to load the okay. So let's get rid of this. The EBO thing. Let's get rid of the EBO. Good. Nice. Nice. I have the vertexes. I have the array object. I have the buffer. No need to deal with Fragment Shader. And ignore the Fragment Shader entirely. We just attach the vertex shader. Modify the vertex shader. Accommodate that fragment shader. Going to output just zeros, just black stuff. If it gets evaluated, now we're just going to say draw arrays, and script for it's all black. It's all black. Still black, but I have no errors as usual. Can I get a white picture, for example? Still all black. I'm not having the pixel output. Well, it has been 3 hours and a half, so I'll be ending this this tutorial, but this session for now. I will continue in another session to develop this further, hopefully debug the output and see if I can obtain the pixel color. Thanks for anyone who has been watching this stream. Thanks for watching, and see you around. Bye.